So, this is in continuation of my previous lecture on the compact sets. In this particular lecture, we will discuss few properties of compact sets and also relation with some other set completeness and other continuity and so on. Another results. Okay. Closed subsets of a compact set of compact sets, closed subsets of compact sets are compact. So, this we wanted to show, prove. So, let us take an F which is a subset of K, which is subset of X, where F is closed relative to X and Y is a compact set. What we want to show, this closed subset, that is F, which is a subset of a compact set, is compact. So, every closed subset of a compact set is compact, that is what we need to show. So, required to prove is F is compact. F is compact means that it will cover every open cover of F will have a finite subcover. So, let us take, let V alpha be an open cover of F. Open cover of F. Okay. Now, this is our scenario. So, here this is our X D, here this is a set K and here is somewhere F. Okay. Now, we are taking an open cover of F. What is F C? F C will be the complement of F. So, here somewhere we have a F C. This is our F C. Okay. Now, if we take a open cover of F, then some of the open cover will intersect F C also, because these are F C is F is closed, the F C will be complement, will be an open set. So, it will be adjoint to B alpha. So, if F of C is adjoint to the open set B alpha, open cover B alpha of F, then we obtained N. We obtained an open cover of we obtain an open cover omega of X of K, omega of K. This is the open cover of B alpha. Now, some of them will definitely adjoint with this. Now, we are taking the open cover of K. Okay. Now, this open cover omega may contains F of C also some. Okay. So, since K is further, let us see, since K is compact, so every open cover will have a finite cover. So, there is a finite subcollection of omega. So, there is a finite subcollection of phi of omega, which covers K by definition of the compact sets K. Now, the possibility okay. Now, once this omega, which is a open cover of K, and since K is compact, so it will have a finite subcover. So, it means that phi will cover F also. Okay. So, and hence this phi will cover F also, finite sub collection will cover F also. Now, in this phi if the phi c is f c is also a member, then we can drop that. If f c is a member of this, is a member of phi, then even if we drop, we can, then we may drop it from phi. Still the remaining will be the finite cover of f, finite cover of f, still retain an open cover of f, remaining with some, with others, with some more, will be finite cover of A. So, but this shows that this implies that this subcollection of this, a finite subcollection of this open cover B alpha covers F. So, this shows F is compact. So, that is the very interesting. Okay. Now, as a corollary to this, if F is closed, and K is compact, then F intersection K is compact. Okay. Now, proof for very easy. What is it? F is closed. K is a compact subset of X. Every compact subset of A is closed. So, since K is a compact subset of say metric space X D, so it implies that K is closed. Every compact subset of this. Further, F and K is all closed set. So, relative to X. So, this implies that intersection part of this, intersection of two closed set is closed. Again, this intersection F intersection K is totally contained in K, which is contained in X. K is compact, this is compact. So, every closed subset of a compact set is compact. So, this implies F intersection K, which is a closed subset of a compact set, hence it is compact. Okay. So, that proves the, okay, hence it is compact. So, this shows the, okay. Next result in this is also interesting result. If K alpha is a collection of, if sequence K alpha is a collection of compact subset subsets of a metric space, say X D, and such that the intersection of every finite subcollection of K alpha, subcollection of this K alpha, subcollection of K alpha is non-empty. Then the arbitrary intersection of K alpha is non-empty. So, this shows the finite intersection property basically. If K alpha is a collection of compact subsets of a metric space X T, this is our X T, and K 1, K 2, K n, these are the compact subsets of this. K alpha 1, K alpha 2, K alpha n, these are the compact subsets of this X T. And if we take the finite intersection of this, finite intersection of K alpha 1, K alpha 2, say K alpha n, like this. If you take the finite and each finite intersection is non-empty set, then arbitrary intersection will be non-empty. So, this we will prove by a contradiction. How will you say? Suppose one of the sets proof, what we will do is, we will pick up one of the sets out of K alpha, say K 1, such that no element of the K alpha, that set K 1 belongs to each K alpha. It means, when you take the intersection of K 1 to K alpha, all intersection sum, at least some of the points of that will be out of it, will remain out of it. Means there are all the not every point of K 1 is none of the point of that set belongs to each alpha, that each K alpha, that is what it is. So, fix a member K 1, then we will reach a contradiction. Okay. Then fix a member K 1 of this sequence of compact set K 1 from the sequence K 1 and put say G alpha as the complement part of K alpha. See, now K alpha is a compact set. So, it is a closed set. So, G alpha will be an open set in X. It is an open. Now, what we assume that this K 1, assume that no points of K 1, no point of K 1, a K 1 belongs to every K alpha, So, this is our assumption. This is very, no point of K 1 belongs to K alpha. It means, when you find it, say picked up the point 1 point of K 1, then at least one of the alpha K alpha will be available where that point does not belongs to, like that. So, no point of K 1 is no point of K 1 belongs to every alpha K alpha. Achha. Since G alpha is an open set and K alpha, and since this collection G alpha is a collection of open sets, and K 1 is a compact set, because it is one of the set which you are choosing out of K alpha, compact set. So, by definition, so K 1 is, so there are G alpha is a collection of open set and K 1 is compact. So, the open cover G alpha of K 1 will have a finite subcover, so open cover G alpha of K 1 will have a finite subcover. Finite subcover means that is they are all finitely many. There are finitely many indices, say alpha 1, alpha 2, alpha n, such that the K 1 is contained in G alpha 1, G alpha 2, G alpha n. Okay, this. But fine. Now, if we, this is a 1, but k alpha I intersection G alpha is empty, because what? Because the G alpha I is taken as the complement of k alpha I. So, if I take the k1 intersection this, so this implies k1 intersection with k alpha 1 intersection with k alpha 2 intersection with k alpha n, then this will be empty set. But what is this? This is a finite intersection of k alpha, but this is this, so this is a finite intersection of k alphas, is it not? That is, if I picked up the finite collection of this set k alpha, then this are the finite. But what is the condition? If k alpha is a collection of the complex subset of metric space, such that intersection of every finite subcollection is non-empty. So, which contradict our assumption that intersection of every finite sub collection of k alphas is non-empty, because it is coming to be empty. So, it is contradiction, and contradiction is because of our wrong assumption that k1 is one of the member out of k alpha is there, which has a property that no point of k1 belongs to every alpha. So, this implies that no such k1 is possible. It means that if we picked up, it means whenever you take the points, it is belongs to at least one of the point, at least it will belongs to all of that alpha. That is what is saying. Okay. So, this is only possible, that this implies that the arbitrary intersection of k alpha over alpha is a non-empty set, because our assumption is wrong. Assumption is that there is a some k1 which has a property, assuming that no point of k1 belongs to every alpha. So, if you picked up one point, then at least one of the alphas are there where that point does not belong. So, this leads to a contradiction. It means whatever the point you choose, it will belongs to every alpha k alpha, hence the intersection will be non-empty. So, that proves the result. Okay. Now, consequence of this is the following results. As a corollary, the corollary is what this says, if Kn is a sequence of non-empty compact sets K, if a non-empty compact sets such that Kn covers Kn plus 1 and so on, Kn plus 1, where n is 1, 2, 3 and so on. Then the arbitrary, then the countable intersection of Kn 1 to infinity is not empty. The proof is follows from there, because what is given? K1 contains K2, contains K3, contains and so on. So, this is our K1, here is K2, here is K3 and like this. So, if I take any finite collection of Kns, then their intersection is non-empty. So, clearly the intersection of every finite subcollection of Kns of subcollection is non-empty, and Kns are the sequence of compact sets. So, by previous theorem, the the countable intersection of this 1 to infinity is non-empty. That is proved. Okay. Now, we have another results. This result will also be used if E is an infinite subset of a compact set K, then E has a limit point in K. So, let us suppose the contradiction. Okay, we prove again by contradiction. So, let us say proof. Suppose no point of K is a limit point of E. So, suppose no point of K is a limit point of E. It means what? If no point of K is a limit point of E, it means if we take each K, that is then each at each Q, each point Q belongs to K, has a neighborhood, say V Q, which contains at most one point, that is the Q itself, one point of E, that is Q itself, central. Because if suppose it contains infinitely many points, then Q becomes the limit point of it. So, that gives the contradiction. So, suppose it contains at most one point. Now, if I take the finite subcollection of this, then clearly the finite subcollection of these neighborhoods V Q will cannot cover say E, cannot cover E, because this is our K and E is this. Okay. Now, what we are assuming is no point of K is a limit point of this. So, suppose I take a Q here, then this neighborhood Q, will contain a neighborhood which does not include the other points of the Q. So, because Q is not a limit point, so at the most it will contain only the point. But since E has an infinite collection of the points, so a finite number of the disks open cannot cover E, because this will only have a finite number of points available in this, cannot cover E as E is infinite set. So, if this neighborhood cannot cover finite, it can also not cover K. So, obviously, this neighborhood cannot cover finite subcollection of these BQ cannot cover K. But what is K? K is compact. So, every open cover must have a finite subcover. Now, BQ, we are taking a open cover for this. So, it cannot cover BQ. So, if finite subcover must cover Q, which is contradiction, because it does not cover Q. So, this contradicts the compactness of K. Hence, the result follows the result. Okay. Now, another two theorems are there. Of course, just one more theorem, and then proof is immediate. If In is a sequence of intervals in R1 such that the INs cover In plus 1 for n is 1, 2, 3, then the intersection of In 1 to infinity is non-empty. The proof is very simple. Suppose I take An, Bn, a closed intervals, and let E be the set of all Ans. Then obviously is non-empty and bounded above by V1, and so let supremum of E is suppose X. Then clearly Ans which is less than equal to Am plus 1, which is less than equal to Vm plus n, which is less than equal to Vm holds. Therefore, when you take the supremum of this, we get X is less than equal to Vm for each m. But An is already less than equal to X. So, what does it show? This shows that X belongs to Im when m is 1 to 3. So, we get the finite intersection of this non-empty finite subcollection of Im, intersection of this is non-empty. Therefore, the arbitrary intersection will also. So, this proves the result. Thank you very much.